Hello, this is the first week of Psych 230, Measurement and Statistics. This week's lecture is designed to acquaint you with the basics of the research process, with frequency distributions, and with basic statistical models. Why do we study statistics? Who cares, right? Well, statistics helps us make sense of our data. Statistics also helps us make inferences about our data. That is to say, make predictions from our data. Suppose we had a coin and we flipped it 100 times. If the coin came up heads 80 times out of 100, could you say the coin was fair? What if the coin came up 60 times out of 100? What if 50% of the people in the placebo condition get better and 55% get better with the medication? Can we say that the medication works even a little bit? Statistics tell us how much the coin should come up heads if it is fair, and how likely it is the coin is fair based on the data we observed. Again, statistics are a way to understand our data, to make sense of it. This course is going to cover statistics for quantitative data. Quantitative data is anything we can measure. Qualitative data is a little different. Qualitative data is also measured, but usually the sample is much smaller and the data focuses on qualities rather than quantities, which is why it's called qualitative. Case studies would be an example of qualitative data, and we're not going to talk about those, that kind of analyses in this course, although there are statistics for that kind of data. Descriptive statistics. So statistics fall into two major types. Descriptive statistics are just that. They describe the data. We don't make predictions really with descriptive statistics. For example, if the coin came up heads 51 out of 100 times, the average coin flip is heads. Descriptive statistics simplify and summarize our data. Inferential statistics use a sample to describe a population or to predict a population. For example, we could use a sample of coin tosses to tell us whether a certain kind of coin, to tell us whether or not a certain kind of coin is biased, how biased the coin is, and these would be inferential statistics. Okay, we could take a few coins, see if they're fair, and then make some kind of inferences or predictions about that type of coin. Okay, so let's say we have a few of these Roman coins that are from 2000 BC. Let's flip them a few times, see if they're fair. If they don't seem to be fair in those three coins, then we can say with some confidence that maybe Roman coins weren't fair when it came to coin flips. Interestingly, there's a body of evidence accumulating that also suggests that a lot of what our brains do is actually some kind of statistical analysis. The brain might do this so it can predict the world. So let's take a few minutes now to review the syllabus. All of the materials for the course as of today will be distributed via D2L. If anything changes and I decide to distribute materials through some other way, you'll be notified via, you guessed it, D2L. These videos, for example, will be posted to YouTube. They won't be through D2L. We will cover one module per week, and there will be one exam each week that will cover the previous module. There will be 5 exams total, and the last exam will consist of about 20% new material and 80% of the old material. The highest grade in the class will be equal to 100%. This is curving. I'm going to curve based on the highest grade. Anyone with 90% or more of that highest grade will get an A. For example, if the highest grade in the class were an 88, then anyone with more than 90% of an 88, in this case 90% of an 88 is a 79, those people would have an A, anybody with more than a 79. In other words, the grades are curved, like I said already. Makeup exams will be oral exams administered in my office and will be completed no later than the last day of class. If you're going to take a makeup, I expect you to have a pretty good reason and some documentation if you can. Well, yeah, I think I do expect some documentation, and a good reason. Please read the section of the syllabus about emails, okay, and follow those guidelines if you want me to respond quickly and effectively to your emails. There's just a few suggestions that I make. They're pretty easy, just to keep things nice and professional and efficient. There's going to be almost no mathematics in this course, at least in terms of actual computation, hand computations, things like that. We're going to review some formulas, and you may be expected to know kind of what the formula means conceptually. I'm probably not going to ask anybody to write down the formula. If I do, the tests are going to be kind of open book, open note anyways. So you should have no problem copying down the formula from these slides into your test. Having said all that, so even though we're probably not going to be doing any hand computation or anything like that, it's still probably going to be beneficial to refresh yourself on the orders of operations shown here in the slide, and there's some other math review materials in your textbook on the first couple of pages, and these are going to be good if you've forgotten your maths or if you just want to brush up, just so you kind of, again, you can look at the formula and maybe have an idea of what it's doing in a conceptual sense. Make sure to read this section on the research process. We're going to talk about the research process more in depth next week when we discuss philosophy of science and hypothesis testing. But basically, how the research process works is we start with an idea. We have an idea about how the world works, and that idea, for us to use in research, it has to be a falsifiable idea. Falsifiable means we can design a test of that idea, and that if the idea were wrong, the test would tell us that the idea is wrong. Okay, so we want to be able to, like the word suggests, falsify that idea. Now, based on that data, the data that we collect, we either confirm or disconfirm our hypothesis. Usually, however, the hypothesis is neither totally confirmed nor totally disconfirmed. So usually what happens is we have a new idea that accounts for the data better than the old idea, right? We've made some adjustments to our idea based on the data that we've collected. Then we test this new idea, okay, and we try to falsify it, review our data, and the cycle continues. It sounds simple enough, but as you'll see, this is actually a relatively new idea. There are some ins and outs to it. The modern scientific method has really only been around for about 50 years or so, although the philosophers have been talking about science in one way or another for about 2,000 years or more. You know, this epistemology, how do we know things, that kind of idea has been the topic of talks by philosophers for a long time. So when we have a scientific question, we usually have one variable that we think predicts another variable. The predictor variable is called the independent variable. The outcome variable is called the dependent variable. Sometimes it's not entirely clear which variable is the dependent variable, which variable is the independent variable, and this is especially in the case of a correlation, where we're not really sure which direction the effect is going, because the correlation is going to be the same regardless. We can measure the IV, that is independent variable, and the DV, dependent variable, in different ways. And there are levels of measurement. Nominal measurement is a category with no discernible ordering. You wouldn't say that blue is more bluer than red or better than red, for example. Similarly, gender, race, and psychiatric diagnoses are also nominal variables. Ordinal measurements are ranks, but the space between the ranks is not necessarily the same. For example, in a foot race, the distance between the first and the second place runners may or may not be the same distance as the distance between the second and third place runners. Interval measurement, on the other hand, has equal distances between intervals. And interval measurements are oftentimes self-report questionnaires, although it's not really clear whether the distance between a happiness of 1 and 2 is the same as a distance between 2 and 3. Who knows? but we kind of tend to assume that they're the same interval distance. Ratio measurement has a meaningful 0. For example, 0 on a happiness scale doesn't really mean much. What does it mean to have 0 happiness or 0 cognitive ability, 0 IQ, something like that? Doesn't quite make sense. Whereas 0 weight or 0 temperature, that actually means something, and we can make sense of what that means. Well, after we collect data, we can when we collect data, we can collect that data between people or within people. We can collect data so that we can compare between two different people or compare 2 different time points within a person. In a between subjects design, we might give one group a drug and another group a placebo, or one person a drug and one person a placebo, and we can compare the 2 groups or the 2 different people. That's a between subjects or between groups design. In a within subjects design or repeated measures design, we might give a person a placebo and then give the same person a drug and compare the before and after effects for that person.